and down. And we just completed our first year in aerospace engineering at Polytechnique Montréal. We're here today to look for an investment of your part of $8 billion in the project in exchange of 20 years of good aviation. The case that we've been studying for the last month consists in the conception of a brand new aircraft that can carry a payload of 35 tons from Montreal to London. This may seem pretty simple at first sight, but the tricky part is that the cargo is a highly perishable one that depreciates at a rate of $20,000 per hour. So we gotta go fast, we gotta be efficient, and while keeping a low environmental footprint. Thus, we are really proud to show you our novel concept of a cargo plane, the flying wing, the wing.
As you can imagine, there's a lot of systems in our aircraft. We have two engines placed on each side of the bubble, which is the increasement on the middle of the plane. We are going to use rake wing tips. On the inside of the plane, you can also find batteries and biofuel, as well as an integrated UAV avionic suit. Here is the weight evaluation for our aircraft, which has the maximum takeoff weight of 90 tons. As you can see, the cargo with 35 tons takes a big place in the aircraft. But when we're coming back from London to Montreal, then we have a lighter airplane which will help us to reduce the fuel consumption.
I'll go ahead with the aerodynamics and performance, the choices, our methods, and the viability of our solutions. So I'll just make a little brief on the design step. First of all, we establish our philosophy, what we need in order to suit our need. After that, we've come up with a solution, the flying wing, and after that, we do the evaluation of the weight. Moving on to the main aerodynamics consideration, the general geometry of the wing, the target cruise speeds, in order to make the detailed aerodynamic calculations that you can find in Appendix A on our technical report. And finally, just a review of the cost and availability of the solutions. Yeah, the design philosophy, as we've mentioned before, these are the criteria for the mandate, so we can move quick. And the solution, why did we choose a flying wing? First of all, the big advantage of flying wing is that all the structures contribute to the general lift of the aircraft. That means less form drag, and which leads ultimately to a lower fuel consumption than conventional airplanes. So here's a really simplified sketch of our wing. We can see that we have a wingspan of 40 meters and a central chord of 10 meters while keeping a sweep angle of 35 degrees. At first sight, we see that the surface, the wing area is way bigger than the chord compared to conventional flying wings. But that is for two main reasons. First of all, the payload is heavy compared to the structure carrying more than usual. And since we're using electrical hybrid engines that we'll talk about later, the thrust given by them is significantly less. So we have to have a bigger surface area in order to fly. Here are the main aerodynamics considerations. I'll pass kind of quick. The cruise speed is Mach 0.85. I'll talk about it later. The main aerodynamics data at takeoff, like I said, you have all the detailed drag force and drag coefficient from expressant, from induced drag, from form drag in Appendix 8. If you're interested, you can look. And just to know, we have a LD ratio at takeoff of around 8.9 and at cruise speed of around 26, 27. So yeah, there are data at cruise speeds. So the aerodynamic conclusion, we have very low ratio of form drag and induced drag. That because since our profile is very aerodynamics, we have less form drag. But because the plane is relatively heavy, we generate more lift. Thus, the differential pressure around the wings is higher, and the induced drag is higher too. That's why we integrated. That's why we integrated rake wing tips to reduce air vortices at tips and reduce the induced drag. And we choose to set the max speed, the cruise speed at Mach 85 to minimize shockwave impacts on the bubble, on the great crescents to put the cargo inside, because the flight will be too unstable if we decide to break the speed of sound. Unless we get expertise from the blood team. I hope you will invest in our company. Yeah.
Alright, so there are three wing control surfaces on each side of the wing in order to control the altitude and the direction. We're also planning to use differential thrust to increase our maneuverability. And as you can see, we place the motors on the front in order to reduce the risk of deep stall that can occur on a flying wing.
So I'll just go with the performance. I'll pass quick because we don't have a lot of time. But here's our detailed data. You can give a look. But we have a fuel consumption of 7.5 tons with the loaded flight, and 6.5 tons on the return, which is really low because of the electrical engines that Alexander will talk about. And the average time on Montreal-London is 6 hours, 40 minutes, and on the return it's 7 hours, 25 minutes. So we can switch, and we can switch. And finally, no, here, can you share? And finally, we can provide a very low fuel consumption, and given the payload of 35,000 kilograms, we found that the flying wings was the only viable solution in order to reduce the aerodynamics impact to use these electrical engines.
All right, I'll be covering the propulsion and avionics and the subsystems of the aircraft. So here you can find your traditional, you can find your traditional turbofan engine that you can find in almost any conventional aircraft on the market nowadays. However, while highly efficient, it still burns a lot of fuel. So our solution that our team adopted, we opted for a hybrid design engine that was heavily based on the HFAN engine concept developed by Boeing under Sugar Bowl concept. So basically, when we say a hybrid engine, how it works, we're using fuel and electricity to run the engine. In details, how it works, there would be this is the electric motor that would be fitted on the main shaft, and that would permit the engine to, while using electricity, burn less fuel for about the same thrust produced. So that's why we have less fuel burned than a traditional turbofan engine. So that's it mainly for the propulsion. I'll be also covering the avionics. So as we said, I don't know if we said it, but it's an unmanned aircraft also. So what we will be doing is we're going to have a satellite data link in order to ensure communication with the plane at all times with our ground station in Montreal and in London. We also have a fly-by-wire system for two main reasons. First of all, it's a flying wing. So we need to have, it's a flying wing. So in order to ensure stability, we must control the roll factor. That's why we need a computer to do it. A pilot wouldn't be able to fly the wing by itself. And also, since we don't have any pilot on board, we cannot have any manned hydraulics. That means everything has to be done electrical. That's why we have high-performance lithium-sulfur batteries mounted on board. Also, we thought it would be a good idea to incorporate solar cells. These are not your traditional solar cells. These are graphene solar cells. The difference between these and the traditional solar cells is that it weighs a lot less, but the efficiency you're getting control factor efficiency. So compared to traditional solar cells, it's about 40%, you're getting only 15.6. That might not seem a lot, but we can still recoup, we can still power our avionics suite with that electricity and part of our electric engine while recharging the battery to the flight. When it's a sunny day, of course, if we're not flying at night. So that's it for the graphene solar cells and cartridge stuff.
So with the structure and the cargo, we decided to, the design would be fast and we would like to implement it in all the airports. So we decided to use a conventional cargo loader, which is just going to take the cargo, bring it to the level of the airplane. The back of the bubble is able to open itself. Then we can slide all the cargo on the rail and then fix them in the wing. So as you can see on the slide, the picture down there, you have the three cargo places inside. Which is one of the problem because all of the weight of the aircraft is mainly placed in the bubble. So in order to be able to have a structural, in order for the plane to be structurally good, we are going to use composites Metal matrix composites will probably take the floor of the aircraft, and we'll also put it in the critical sections. The rest of the aircraft, by the wing I mean, are going to be carbon nanotube composites and graphene sheet composites that will be developed in the 2025 year frame. But if it's not ready, we plan to use carbon fiber.
Now I'm going to cover the impacts on the environment, which is going to be increasingly important as we go in time with the climate changes and everything. So, to reduce the GHG emissions, the greenhouse gases, we chose to use biofuel. Biofuel we chose is bio-SPK, which means synthetic paraffinic kerosene. This fuel has a few advantages. The first big one is it's renewable, because it's grown from plants. The second advantage is that it has a carbon neutral combustion, because the carbon emitted by the combustion process is reused in the photosynthesis process on the plant. Next, tests have shown that we can have a higher fuel efficiency with this kind of fuel, and it has a lower health risk than conventional fuel. Next, talk about reduction in GHG emissions. Here we have a chart of the entire life of the fuel, comparing the conventional petroleum jet A fuel and the camelina-based bio-SPK. We have an incredible saving, which is 84% in the GHG emissions, which is very surprising. But as we see here, as I mentioned, there's a zero here, net combustion, because the emissions are used in photosynthesis process. So that's why it's a pretty high saving. Next, for the materials, we use a lot of composites for many reasons. In the fabrication process, there's a lot less waste in composites than in traditional metal machining. So there's a lot less scrap there to recycle and reuse after. In the life cycle of the plane, carbon fiber is a lot lighter than aluminum, so we save a lot of fuel there. And in the hardest part, which is the recycling, we can use different methods that are currently being researched. One of the methods is to shred the fiber and reuse it as a filler compound, or just melt it into a new piece. Or use pyrolysis process to remove the resin from the fibers and reuse the fiber itself into a new virgin fiber. Now, for the part that probably interests you most as guidance, the cost and profitability analysis. This here we can see a chart of the biofuel that we use. In the blue line here you can see the cost of the kerosene that it's estimated to increase over time. Here the little red line is the penalty applied on GHG emissions that are implemented by governments nowadays. But here we see the cost of the biofuel, which is right now it's a lot higher because there's less technology around it and everything. But with the market development and the demand increasing, you can see that the cost is going to be lower actually than currently than jet fuel. So that's why in the contest it was said that the fuel was $5 per gallon, but we estimated that it's going to cost $4 for this biofuel, and we use a 50% mix, so it's $4.50 per gallon. Now, and we have the cost. Yeah. The cost of operation. The main part is the cargo depreciation, because it's a fairly slow airplane at Mach 85. The other big part is the fuel consumption. Even if we use biofuel and electricity, it's still a big piece of the price. And using the specific constraints of the competition, which was 10 round trips per month, we calculated a profit of 8.41 million. Next, 8.41 million covering our 8 billion development cost. It's going to be pretty long to reimburse your investment with only one plane, as you can see, it's going to take 80 years. But as we build more planes, development cost doesn't increase, it's just the fabrication cost, which is about 100 million per plane, which we estimate. So if you can look at the graph, with 10 aircraft, it's going to take only 10 years to refund, and then it's going to be 8.41 million profit per month for the rest of the time of the aircraft. So now it's the question period.
I guess I'll start seeing this over last time. When I look at your design, I look at the way the aircraft is modeled and the fact that it's all concentrated on the wing. You don't have any critical control surfaces, no empennage, and it's great. When we look at it and we see it in popular science, it looks fantastic. It looks like a way of the future. But practically, have you considered the logistics of just to be able to load and unload an aircraft like that?
Yeah, but we were inspired by the Beluga design, and we thought that it would, since the material used on the rear back of the bubble is kind of light, and we have a good structure made from new composite material to support the movement, we thought that it should be possible to do it.
Okay, I'll reformulate my question. Have you looked at the logistics of being able to load and unload? What I mean by logistics is time to load, time to unload, the type of equipment that you need to be able to carry the load to and from the aircraft.
Well, yeah, we checked it, but there's also a rail inside of the cargo to accelerate the movement. But since we only take 10 round trips, there's a lot of time between the loading and the unloading. There's no like a rush during the competition, so we didn't went all in to calculate this time.
And in our cost planning, we're not renting the cargo loader. We will buy one. That's our prediction. So it will be more cost efficiency. It will be more cost efficient like that. And the bubble is pretty voluminous. It's like 2 meters high. So your comment is really pertinent. But I think it could be possible. It's innovative. It's ambitious. But I think it could be possible.
So you'd have a loader with a specific type loader in every airport that you'd be landing.
Well, in London Heathrow, well, we considered for London Heathrow and the Montreal airport. But yes, it would be a consideration. If you want to export the concept elsewhere, yes, we would need to appropriate specific cargo loader. But
we were considering 2 main airports.
Thanks.
A question first from Mr. Escarmo, please.
Okay. Nice presentation, well structured, design data, that's really interesting. I had a question regarding, apart from the UAV, again, certification issues that we already discussed. In terms of the engine, your electrical hybrid turbofan, that's interesting. Frankly, it's the first time I hear about it. In terms of data, maybe you have it in appendix that you can look. It's interesting to see like comparison between like the gear turbofan, for instance, or.
I was expecting the question, so I prepared a backup slide. But that was another backup slide, but always can prepare. These are the main specifications of the engine. As for, it might be easier for you. These are the common specifications you would find in an engine. The way we came up with numbers, we didn't come up with these numbers. These were the numbers that we took from Boeing's trigger ball concept. They made the analysis, they said it was possible. And why we chose this particular engine is when we calculated our drag on our aircraft at cruise speed and during the various phases of the flight, we found that for the thrust provided by these engines and with the batteries we chose, this would be a perfect match for our solution. So that's pretty much it. And it also it features a lot of advances in engine technology. We're talking about composite flying, composite nacelles. Since the study dates back from 2011, we didn't have these engines on the market. Now you're starting to see these engines on, for example, the new GE Next engine is featuring a composite fan with a titanium alloy. So you're starting to see the thing. And frankly, Boeing did the risk assessment of how possible this engine would be in the 10 years time frame. And their biggest scare, you know what? Was the batteries. It wasn't the engine, it was the batteries. They were scared, and we looked in the batteries, and we saw research, and lithium sulfur batteries were recently surfaced 2 years ago. They feature everything we need. They feature the correct wattage that we need. So I hope I answered your question.
In 10 years from now, the energy source plus the
Yeah.
hardware will
Yeah, it will merge.
is possible.
Yeah.
Well, first of all, well done, Ecole Polytechnique Montréal. I thought that was a great presentation. I thought what you did very well at the start was clearly demonstrate that you understood what the problem was, and you had a nice, clear design philosophy, which was good to see. I've got a first question, and then my proper question. The first question is a question I get asked all the time. Why the name, the whale?
Okay. Yeah, you do.
But the whale is it's not a joke, but you can see first the bubble, the cargo, because our first idea was to extract the cargo from a lift, which was like the jet of the whale, and if you look, if you have an upper view of the plane, it looks like a whale tail, and the first prize is to go to Wales.
Very good. I like that.
Projection.
So here's my proper question. You've got an impressive amount of aerodynamic data in you, and if I had to look at the appendix, and it's kind of all backed up there. You talk about specific things like the Oswald efficiency factor, the Oswald factor, or the Oswald efficiency factor, and you give it a value of 0.7. Perhaps this is a slightly naughty question in front of an audience like this. First of all, what is the Oswald factor? Okay, and second of all, how did you get the number 0.7?
Yeah, I've talked with an aerospace professor at Polytechnique, and he said to me that if we got a flying wings with no tails and no shredder, we should take 0.6 from Oswald coefficient, which describes a bit the aerodynamic profile. I'm not sure. I read a bit about it, but in the time frame, I was more focused. I did more focus on calculations, and I take the assumption from the professor who is more experienced than me. But
Good answer. Just trust your professor.
yeah, and you're more experienced. and I said I'll just operate value a bit to reduce my drag, because the more the Oswald coefficient, the bigger the Oswald coefficient is, the less drag you'll have. So
Okay.
it's the I remember. It's the ratio of your hyperbolic distribution of lift on your wing. Is that it?
That's pretty close, yeah. You're always looking for number one, but one is the best you can get. So I just wanted to get your answer. Okay, great. I won't quiz you anymore.
Two more questions, perhaps?
So may I ask, have you thought of the cargo compartment, right? Will it be pressurized or unpressurized?
That's a good question.
Given the highly perishable product you're transporting, and you're already losing 14% of this cost, or 14% is not that bad.
That's a fairly good question. To be fair, I wasn't expecting that. What we were expecting, the pressurization, since it's unmanned, we didn't need a that's what we thought, we didn't need a pressurization system on board, since there's no people on board, that's why. But since now you're here, and we don't have any windows also, now since you're bringing up the perishable pallets, I thought the pallets would be pressurized. Probably, well, it depends,
It adds up weight to the pallets?
yeah. Well, to be honest, I'm not entirely sure, but it would be something that we need to develop in the future, because it's still a fairly new concept. We focus a lot on the aerodynamic data. If it was possible to fly with the engines that we found, with the configurations, everything,
And structure-wise.
structure-wise, it was everything, that was our main concern. The pallets per se, we would think it would fit in the aircraft. So I hope that answers your question.
Yeah,
That was a good question.
question.
Right, so last question from Martin Lafleur.
Okay, so you mentioned $8 billion in development. Billion?
Yeah,
That's okay. 80 years to see our money back?
for one.
Oh, for 1 year. Okay, that's okay. That's fine, that's fine. My grandchildren can see.
You'll be refunded in 10 years, if you build it.
Okay. So, a wing concept, hybrid turbofan engine, that's very innovative, solar cells, carbon nanotubes, biofuels. What is your plan for the certification of all these different technologies? Large question.
Well, for certifications, we use a lot of new technologies as you see. So it's going to take a bit more time than just take an old aircraft and just modify something. So it's going to be harder to certify. But we're confident that in the 10-year time frame that we have until the 2025, technologies are going to mature, and that the Transport Canada or the FAA are going to approve them for the use not only in the well but other commercially available aircraft. So that's
Just like the lithium sulfur batteries has just been accepted, I think, to.
Yeah, the lithium sulfur batteries are not yet commercially available. There's still a lot of research being done. The efficiency that we saw, I think it was 500 wattage per hour that was done in laboratory at Oxford. These are efficiencies that we're already obtaining and that we can already fire them with this. So in 10 years, we can get more efficient energy density with less batteries, just reducing weight, and we can, well, it costs less, and so.
And it will be the final word from Polytechnique Montréal. Thank you very much for your very good work.